Welcome to the CERIAS Security Seminar here at Purdue University. Today's speaker is Jong-Soo Koo, who is actually a PhD student here in the Computer Science Department. And he will talk about process implanting, a new active introspection framework for virtualization.
Thanks. Thanks for coming. Today I will present a paper, Process Implanting, a new active introspection framework for virtualization. This is a joint work with Drayden and Dongyan Shi from Purdue University and Xuxian Zhang from North Carolina State University. So first, let's take a look at the motivation for a paper. The malware has spread across the world for so many years. It can disrupt the normal operations of your application, and it can steal the sensitive and confidential information from your computer. And it can also gain the unauthorized access to your computer by exploiting the vulnerabilities of the kernel. So malware defense has always been a hot topic for the research, not only in the academia, but also in the industry. So we can simply classify the existing approaches to two categories. The first one is an in-box approach. The basic idea is to place a monitoring engine inside the machine and use this monitoring engine to monitor the process that is running inside of the operating system. And it has an advantage is that it has in-context execution. It means that it can call the APIs that has been offered by the operating system kernel, and it can also leverage the services that has been offered by the operating system. And it also has in-context information. It means that it can read and write the physical memory directly, and it can also know the hierarchy of the file system. The second advantage of this approach is it is agnostic to different OS release. So for example, we can install the antivirus software on the Windows XP, and we can also install the same one without any modification on the Windows 7. But we also know that there are some limitations for this work. The first limitation is that it has an obvious footprint. It means that the monitoring engine will leave, when we install the monitoring engine, and there will leave some footprint in the operating system. And it is very easy to be detected by the other process that is running on the same machine. And then, so it is very easy to be tampered by the malware because the malware and the monitoring engine are running on the same privilege level. And this, when sometimes the rootkit, when there is a rootkit as a malware, and it can compromise the whole OS kernel, and then it can disrupt the system core, and then it will report the unreliable results to the monitoring engine, and then this results cannot be trusted by us. So there is a trend in the research that want to transit from the in-box approach to the out-of-box approach. So the basic idea is to move the monitoring engine from the operating system to out-of-box, and then add an additional layer of the hypervisor to running under the operating system, and use this monitoring engine to monitor the execution of the process and the operating system kernel in the box. So it has advantages that it can monitor the process and the operating system kernel transparently. So the process and operating system kernel cannot know that it is being monitored. And it is very hard to be tampered because the process running inside a virtual machine cannot break out of the box. It is contained in the virtual machine. So, but it still has some limitations. The first limitation is the semantic gap, because the monitor has been moved out of the box, so it can only see its raw memory, and then it needs to reconstruct all the semantic objects of the operating system. It's just like the process descriptor and all the page tables and the file system hierarchy, and use this knowledge to find the interesting objects in the virtual machine. And the second limitation is that previously, a lot of research has been done on the emulator because we can capture every execution in the instruction level in the emulator, and we can instrument every instructions. But in this case, but there is some problem for the emulator is that emulator has some performance overhead. And so a lot of research has been transited to the hardware virtualization. But the problem with hardware virtualization is that it will run directly on the physical CPU without any interference from the hypervisor. So it will hide a lot of details. So it's very hard to capture every interesting events inside of the virtual machine. So the third limitation is that when we implement the monitoring engine, and then the tools highly rely on the implementation of the operating system kernel. And if the layout of this operating system has changed, and we also need to re-implement our old tools. So this is a lot of work to do. So in that case, we have proposed a process implanting framework. It is a hybrid approach of both the in-box approach and the out-of-box approach. So we want to get the in-box context. We will dynamically implant the process into the guest VM and run the implanted process inside the box. And we also want to get the active introspection. So we not only we want to passively monitor the execution of the operating system and the process, and when we found some malware, we also want to quarantine the malware and clean up the system and do some recovery job. And the third one is that we want to avoid the semantic gap. So because our implanted process is running inside of the virtual machine, so there is no semantic gap for our process. And also there is a lot of existing excellent tools for the in-box approach, and we just want to reuse them without any modification. So, but we also want to gain some out-of-box protection, and we want to get a protection from the underlying hypervisor. And because the hypervisor will inject our process into the virtual machine, so it is aware of the execution of our process, and it knows when we need to stop our implanted process. And our process should also be stealthy to the malicious process. It means that it is hard to be detected and hard to be subverted. So let's take a look at a basic idea of this framework. So we see from the picture, and we have several processes that is running inside a virtual machine, and we place our process implanting module on the hypervisor. And we also prepare an implanted process binary on the host. So in the first step, we will select an existing process as a victim process. So we colored it as red. And then we will save the victim process context. It means that its running context is for the restoration afterwards. So we save the victim context on the host. It contains CPU registers and the memory mapping. And then we will replace the victim process with the implanted process. We will map the implanted process binary into the memory, and then launch the implanted process and use it to replace the victim process inside the virtual machine. And then we will create a communication channel between the implanted process and the process implanting module, and then, in that case, the process implanting module can notify when our process should be stopped its execution. And then, when we finish the task, we will terminate the implanted process and restore the victim process from the saved process context. So we just put it into it, and then we run it again from the stopping point. So then I want to give some features for the design of our implanting framework. And the first design is that the implanted process is posing as a victim process. So it will reuse all the victim process data structures. So there is a question, why not create a process from the very scratch? So it is very hard to allocate the data structures from outside of the box. And it is very hard to clean up all the data structures when the implanted process has finished its execution. So we use data structures like the process descriptor of the victim process and all the page tables and all the heap. And we also, in that case, we also can keep the stealthiness of the implanted process, because from the system view, there's no difference from the implanted process and the victim process. The content has been changed, but from outside it is the same. And forking a new process is not permitted in this case, because if we fork a new process from the implanted process, and we will leave a very obvious memory footprint in the operating system. For example, we will create a new process descriptors in the operating system, and it is very easy to be detected by other malicious process. So this one is not permitted. So the second design feature is invisible memory space. So we see from the picture and the victim process page table, and then this is the original physical memory of the guest VM. It spans from the 0 to the memory size of the guest virtual machine, and this one is allocated during the boot up. So the victim process page table, there are some pointers from the page table to the user stack, the code segment, and the data segment. So we cannot allocate the memory inside of the box, so we just choose to allocate the memory outside of the box. We will allocate 3 memory blocks. The first one is for the implant process user stack, and the second one is for the code segment, and the third one is for the data segment. And it spans from the memory size of the virtual machine to the memory size plus process size. And it is allocated during the implanting period. And during the implanting, we will change the mapping from the victim process page table, and we will point to the user stack from the victim process to the implanted process, also the code segment and the data segment. And then we will launch our implanted process and begin to run our old process. Then we will talk about something about the timing of the implanting. So when do we need to implant our process into our guest VM? So we choose to intercept every context switch of the operating system. And if the victim process is the next scheduled process, and we will choose it and replace it. So what is the safe timing? So if this context switch is caused by the system call, it means that this victim process want to execute a system call. And at that time, we will set the instruction pointer backwards during the restoration period. And then we will re-execute this system call. And the victim process will not lose the context for the system call. So if the victim process is uninterrupted, and we just leave it silently without implanting. And the third situation is that if this context switches happen in the kernel mode, it means that this context switch is caused by the kernel thread. So we choose not to implant it, because we only save the context of the user thread, but we do not save the context for the kernel. So we just don't implant at this time. And also we have designed a scenario for the frequency restoration. So what if the malware is capable of scanning the page table of the implanted process? So if the implanted process still point to the implant process memory space, and it is very easy for the malicious process to scan the page table and find that this mapping has been changed by us. So we will recover the victim process states when it is scheduled out, and modify the states again when it is scheduled in. And we only support one virtual CPU, because if there are 2 processes that are running parallel on 2 different CPUs, and then the malicious process can also monitor the execution of our implanted process and can find that our process has been changed. And The implant process is scheduled by the guest OS, but we also have offered a level of protection by the hypervisor. So let's take a look at the animation. So the implant process previously point to the implanted process memory space, and then it is scheduled out by the virtual CPU. And then we change the mapping from the and point it to the victim process memory space. And at that time, the malicious process has been scheduled in, and it wants to scan the page table of the implanted process, and it can only find that it is point to the victim process memory space. So the implanted process memory space is still cannot be detected by the malicious process. Then we can talk something about the coordination from the hypervisor. So what if we want to perform the mandatory restoration of the victim process? So for example, if we trace a process, we implant a trace program into the guest virtual machine and use this one to trace a malicious program. And then when we want to exit this process, and we need to detach it from the original process. So if we do not do this, and then it will still be traced by the victim process, and then it's just like it is traced by a zombie. So the second scenario is that if we implant a multi-threading process into the guest VM, and it will spawn some like children's threads, and we also need to clean up all the children's threads before they exit. Otherwise, when the implanted process has terminated, and then the children's threads will still running inside of the guest virtual machine. So in that case, we create a covert channel between the implanted process and the hypervisor, and the hypervisor will set some control bit at the user stack of the implanted process, and the implanted process will check this control bit periodically. If this control set has been set, and he just clean up and exit. So then we'll talk about the protection by the hypervisor. So what if the malware wants to kill the implanted process? So in the first situation, we will elevate the privilege of the implanted process to the root privilege. We will modify the credential entries in the process descriptor of the implanted process. So what if the malware also has a root privilege? And then we set the unkillable flag for the implanted process. And this unkillable flag is only used by the init process inside of the virtual machine. And init process cannot be terminated by other process, even if this process has a root privilege. And we will also check the unkillable flag all the time to make sure that this bit has always been set, and it will not be changed by the malicious process that is running inside of the virtual machine. So when our implanted process needs to exit, we will not let it execute the exit system call directly, because the system will try to free all the process memory. But this process memory, we have seen that this process memory is out of the boundary of the virtual machine. So if we want to free the memory that out of the boundary of the virtual machine, and it will cause a kernel panic. And also we need to restore the victim process, because we have saved the context it, and we want to restore it from the checkpoint. So our solution is to intercept the process exit system call. We will set the debug register at the entry level of this exit system call, and when it step into the exit system call, it will cause the debug, and then our hypervisor can capture this event, and then we will bypass all the execution of the exit system call. It means that we can set the instruction point to the caller of this function, and it means that it's just like that it is step into it, but without any execution, and step out of this function. And then we will restore the execution of the victim process from the save the victim process context. So we see something about implementation. And the implementation is based on the hypervisor of the KVM. This KVM is a kernel-based virtual machine, and it is act as a kernel module on the Linux and then transfer the whole Linux operating system to the hypervisor. And it is enabled the hardware virtualization. And our host OS is Ubuntu 10.4, and our guest OS is Ubuntu 9.10. So then let's take a look at the evaluation of our framework. And in the first scenario, we have implement a malicious process. And this malicious process is used to read the memory mapping from the proc file system. So we can read the page map of the page table from this proc file system. And in the first scenario, we disable the frequency restoration. And we see that, so we will scan it in an infinite loop. And in the first scan, we see that the victim process is running inside a virtual machine. So the page table is correct. And then the victim process is pointing to the memory space of its own memory region. And then when we do the implanting, and then we will change the mapping of the page table. And then we see our scanner can find that implant process has changed the memory mapping, and the memory mapping has exceeded the max memory of this virtual machine, and it is very easy to be detected by the malicious software. So in the second case, we enable the frequency restoration, and then we scan it again, and all the victim process, it will always point to the victim process when we scan the page table. So the second evaluation is that we implant an ltrace program to trace a malware that is running inside a virtual machine. And the ltrace is a program to track the library function call of the running process. And we will transfer the tracing log from the guest operating system to the host through the hypercore. So we see there are two windows, and this is the malware. Its name is IMSIG, and this is a KVM hypervisor window. And we see that when we begin to trace this malware, and it will first open an infected files and fork a new process and execute the infected file, and then it will delete this infected file. So it is very easy to find the malicious behavior of this malware. So in the third evaluation, we will trace the infected program. So we will first use a Kellen to infect the program. Kellen is an ALF infector, use a segment padding infection, and it will insert the virus code after the code segment. It means we will use a LS program as an infected program. And then we also trace the library function call of the infected LS. And we see that it will compare the strings and use the Kellen's headers and to do the malicious behavior. And then there are a lot of memory copy that is malicious. There's some malicious memory copy inside the log of this process. Then we need to measure the performance overhead of our framework. And we have implemented a micro benchmark. This benchmark is used to read and write the files and allocate and free memory. And we will run it for 1,000 times to measure the performance. And the testbed is Dell Optiplex 755, and it uses Intel Core 2 Quad, and it is 2.4 gigahertz CPU. And we allocated 3 gigabytes for the host memory and 1 gigabyte for the guest memory. So we choose three processes as a victim process. The first one is a GNOME Power Manager, and the second one is VMstat, and the third one is a GIMP. So So in the first case, we just disable the implanting and run our benchmark directly inside a virtual machine and use this as a base benchmark. Then in the second case, we will enable the implanting and then to implant our micro benchmark into the virtual machine and then to measure the performance. And we see that it will not exceed the 10,000 microsecond. And in the third case, we will enable both the implanting and the frequency restoration, and then it will not exceed like 15,000 microsecond. And we need to see that our framework is very decoupled from the implementation of the hypervisor. So when the implanting has finished, and then there will be no performance overhead for the whole hypervisor. So then we will give some discussion of our project. The first one is a trust problem. We don't need to trust the library of the guest VM because we statically linked the implanting process binary. But we need to trust part of the kernel service. It's just like if the implanting process has issued some system calls, and these system calls should be trusted. And we will leverage the kernel integrity enforcers, such as the nickel and the hook safe, to promise the integrity of the kernel. And what is the choice for the victim process? Not all the process can be chosen as a victim process. So if this process cannot be scheduled, we will not choose it. We will not choose it. For example, the idle process, because it will not be scheduled, and there's no chance for us to select it as a victim process. So if this process is highly user interactive, like the browser, and it is not recommended because the user will feel that there is some stop in the process, and it will either to be detected by the user himself. And then if the process starts to run periodically, yes, we will choose this kind of process. It's like the top and the VM stat and the non-power manager. It will run periodically, and it always has a chance to be selected. Then we will give some conclusion of our paper. And it is a general purpose active VM introspection framework. And it will avoid the semantic gap between the guest virtual machine and the hypervisor. And we want to have the minimum impact on the guest system after restoration, because the system will run as usual. We will not change anything when the implant has finished. And we will also offer some coordination and protection from the hypervisor, and use hypervisor to protect the process running inside of the virtual machine. Thanks.
Questions?
Yeah.